Okay, so now let's talk about the complexes you can get. It's like from a Morse-Smale function. And as you recall, it's like when we were talking about Morse-Smale functions, what we were trying to do was to construct a, it's like something like a Morse function, but with additional, it's like genericity assumptions, which then allows you to look at the stable manifolds of the gradient flow of the Morse-Smale function, and then try to form a complex out of that. Okay. So, and in particular, the additional property one adds, it's like to Morse functions in order to get Morse-Smale functions is this notion of transversality of the stable and unstable manifolds. Okay, so transversality sort of implies that when you intersect a stable Q manifold with an unstable P manifold, you get an intersection of dimension P plus Q minus D. Okay. All right. So sort of a further consequence of this is that, of having transversality, is that the boundary of every stable manifold is the union of stable manifolds of lower dimension Okay, and I should say that they're lower dimensional, but they don't necessarily have to be just one lower in dimension. Okay, and we'll see examples of that. Okay, and then the claim is that the set of such stable manifolds form a complex and we can construct this complex one dimension at a time, right? Okay, and the way we're going to do this is that we're going to look at sort of building up the skeletons of the complex, and so the skeleton of a complex basically is just a set of all sort of simplices or cells. It's like it's like a dimension, say k or less. Okay, and you can easily convince yourself that if you look at the skeletons, they themselves are subcomplexes of the original complex. So we're going to sort of do the reverse. We're going to sort of build it skeleton by skeleton. Okay, so you first start with the zero skeleton, which is obviously just a set of sort of zero cells. So you add all the minima because all these minima are basically stable zero manifolds. To sort of initialize the complex. Okay, and then once you have that, you can sort of add the one cells, right? So you add, so it's additive, right? So you still have all these minima. It's like coming from the zero skeleton, but I'm not adding. It's like the one cells, if you will. So add all stable one manifolds. Okay, and so each of this are open intervals, or an open interval sort of glued along its endpoints. To sort of two points in the zero skeleton, which are of course just minima. Okay, and then you have the two skeleton. And as you might expect, you add all stable two manifolds. Each of which is an open disk. And it's glued along its boundary. To a cycle in the one skeleton. And then you sort of keep doing this. Okay? All right. So a few remarks are in order. There's the possibility of degeneracy. Okay. So sort of remarks. So it is possible that sort of the two minima, it's like where you add sort of these stable one manifolds are the same. So it forms a loop. Then the cycle in this one skeleton can be degenerate. So it's really, in essence, a point. So it can be pinched, or even a point. So again, the example to keep in mind for this is the height function associated with a sphere. And of course, there's one maxima and one minima, right? So the zero skeleton is just the minima. It's a unique minima. And then the maxima, right, has a stable manifold which is two-dimensional. So this shows up in the two skeleton. Right, so this is the stable two manifold of the maximum. And you can sort of see that's an open disk. It's like, but then it's glued to just the minima, right? So which is an open disk, open two disk, right? Glued to the sort of the minima. Okay. All right. So sort of the way to sort of think about this is that you have a piece like this, right, which is the stable manifold. It's the stable 2 manifold. And then it's sort of glued, it's like to this point where this part is identified with this point. Okay, so that's basically what's happening in that situation. Okay, so but in any case, it's like you still can you can still think of this as a complex. It's like, and in particular, you can still do homology. It's like on all of this. Okay, and compute other topological invariants, and then in the next part, I'll say something about a bunch of what are called Morse inequalities, which relate the basically it's like the it's like the sort of let's say the topological properties of the manifold with the index associated with the critical points. Okay, right. So let me just stop here for now.